Hi, everyone. Thank you for joining this presentation. So I'm going to do two things in it. I'm going to walk you through the thought process about that we experienced in building a condition-based maintenance system for a particular client. And because it's important how you approach a problem that you need to solve. And then I would walk you also through the actual implementation and some of the aspects of it. And both implementations come from essentially support of military equipment. So some of the data, I won't go into all the details, and I don't know all the details that happen after the fact. But so what is the future of maintenance? So when we first started on condition-based maintenance, they said essentially, don't think what you have today, think what you want to have 20 years from now. And then let's start thinking backwards and kind of come up with the right system about where we want to be so we can start building towards it. Because one of the incredibly difficult things about systems is that you have to make them extensible. And this is actually, when we build them, the last thing we think about. We don't take into consideration how they would evolve. And consequently, we very frequently end up rewriting them, which is very expensive. And the larger the equipment, the larger the machinery, the more expensive such a rewrite is. So what's the future of computers? Strangely enough, we first tried to design robots and computers to look exactly like us. And that has been going for years. And it also is strange how it evolves over time. So the first robot was mentioned in 1921 by Karol Čapek, and essentially it meant forced labor. That's what we were. We were building slaves, mechanical slaves. Now, nowadays, it feels kind of the other way around. We're competing to keep up with the robot. So it's an interesting turn of events. But when you also know it's 1921, when you actually go to the Expo in New York City, the robot that was presented in 1939 in New York City, guess what they wanted to teach the robot to do? To smoke cigarettes. So somebody's shaking their heads. I wonder what would we teach a robot today, actually. I said, what would be? I mean, cigarettes now, today, what? But again, goes down the path to say that we were going for a very long time down the path of actually making the robots and those type of machines look exactly like us. And one of the largest industrial robots manufacturer in the world is Fanuc. They do all the car manufacturing, all other types of industrial robots. And years ago, the founder of Fanuc, actually they're based in Japan, said we can't think of robots as being a replication of how we humans do things. We should actually think of what's the best way for robots to do a particular task or an activity. And his favorite example was, if you want a robot to lift something, you are not going to build a hand for the robot to lift something. You need a completely different approach to it to make it efficient. So we're moving in this direction now, and we're not talking so much about robots, but we're talking much more about intelligent machines. And those intelligent machines that look like us are called the humanoids. And believe it or not, we're more afraid of the humanoids than of the intelligent machine. It's purely psychological. That's a very interesting reaction to it. When in fact the intelligent machines can be much more dangerous than those that are humanly looking. And I don't know if you know, but essentially this is Sophia. She shows up at TV shows and everywhere. She's manufactured in Hong Kong by an American scientist. And it's quite interesting. But we're moving more and more. The point here is those intelligent machines. And so going into the ship story is we had to think, this particular case with the client, what would be the future of ships? And the number one answer was, well, we'll have unmanned ships. That's period. That's what's going to happen. They're going to be at sea. They're going to stay for very long at sea without communicating with us. So how do we build everything for a ship that's in this condition? Believe it or not, once a military ship leaves the base, no data leaves the ship. So for them to take any condition-based maintenance data, any data coming from the operations of the ship, is strictly prohibited. When the ship comes back, that's the point when everything's downloaded and analyzed. So that's an expensive process, so naturally you want to build and say, well, how are we going to do this at sea when there is no communication and no people in it? And this discussion occurred probably 4 years ago, and I thought that we're 25 years away from having an unmanned ship at sea. And guess what? This year in March, the US Army deployed actually the first drone ship, completely unmanned. So clearly we're moving into this paradigm of intelligent, self-sustainable machine. And so the three components that make such a machine are intelligence, autonomy, and self-healing. I mean, that's really what it boils down. So these are the three kind of systems that would allow us to really build sophisticated machines. And when we look from a condition-based maintenance perspective, it is literally about self-diagnosis, repair, repair decisions, and self-repair. Right? It boils down, and so the question is, how do we build all of these things going forward? And again, the reason we're moving to, why are we moving to condition-based maintenance? I mean, what's the big incentive for it? It's cost savings, right? If you have a scheduled maintenance, actually it's well documented that the difference between a scheduled maintenance and condition-based maintenance is about 50% savings. Especially if you deploy some operational metrics that enhance the lifetime of the machine, you're getting significant benefits. And so if you think from a fleet perspective, you have ships at sea, if they're scheduled to come back to shore, you're incurring every 6 months, the ship comes to shore, gets a total maintenance, and etc. When you move to condition-based, you find out that sometimes you don't bring the ship back for a year, right? I mean, that's a very significant saving just from the logistics of the maintenance operation. So this really is driving us with, again, the next stage with the self-repair, the ability to have a long-term missions. Like if you're doing a mission to Mars, naturally you want this mission to be, it will be at a minimum 2-year mission, and it's going to be probably longer than that. So you need to take into consideration the lifetime of the entire operation. So that's how we're working, and we're thinking, how do you get to these things? How does the machine self-diagnose itself? How do you make repair decision? And self-repair is kind of the ultimate goal. And you may think that we're far away from self-repair, but we actually have the first machines that do self-repair. You have the whole digital printing is making this quite possible in various operations. The whole augmented reality fixing of things allows currently for remote assistance in such things. So quite a strongly evolving area of enhancement to the technology. So what is the new information architecture? So if we're going to have a machine that's going to have intelligence, make decisions, and do some actions on itself or on the system around it, the question is, what is the new architecture for such a digital enterprise? And it's not just Gartner, I use them as one of the experts, but essentially all of the analysts have come that we're going to have different kinds of systems, namely 5 different systems that are interrelated, the customer-facing, partner, employee, and the system of things. But what's critical in this new architecture is that actually data and analytics, the platform that would ensure data management and analytics, is put right there in the middle. And so that's the holistic view. That's for the first time we're actually acknowledging that if we're going to build an intelligent enterprise, intelligent operations, intelligent machines and everything, data and analytics has to be at the core, like the brain. The analogy is quite simple with the brain. You need the central processing system that's going to do that. And the even more interesting thing is that these systems have interactions. So you're going to have in the IoT platform the operational control system that has built-in analytics. You're going to have edge computing and etc., everything in here. But these are point-in-time systems that can give you this event happened or it didn't happen. But knowledge is gained when you actually relate events. So we're going to need to connect that information from here with various other systems in order to be able to understand what's going on and to make some decisions about what's the best way to proceed forward. So if you think about a machine, even in the complete automated decision, it still has to have a touch to the entire logistics systems to find out if a part has to come from somewhere and ordered or being delivered or any kind of decisions like that, or manufactured, and etc. So all of these things have to be connected. And that's a step that is hard to take. Enterprises are already doing it. And I'll tell you the difference between when enterprises really get to this point, this is when it gets very interesting and when it gets to a hyper growth. So you can think of one company that's far ahead in that, and that's Amazon. And in a couple of years, it scales horizontally and vertically because of the connectedness of the system. So they can scale horizontally and expand very quickly the market share in a particular market, regardless whether it's selling books or selling groceries or anything else, to expanding horizontally where they moved from books to groceries to now the discussion is about insurance and logistics. This kind of fast, rapid scale effect is due to the interconnectedness of the systems. And that's more important nowadays in manufacturing and especially in the condition-based maintenance, where this is giving companies competitive advantage. So I strongly encourage the thinking around this topic and how this holistic interconnected architecture can be achieved. We all know the costs associated with it, the difficulties associated with it, but we also know the benefits and have to move in this direction. So let's see how it works now from how we thought about it to what really happened. The example I'm going to give you here is one of the companies, Bear, and what they do, two main things, is fleet services and naval-based services. And they keep all of these ships at sea operating and running at an optimal performance. That's really the one thing that they have to do. And here they have a wide range of support services to keep the naval base running. I mean, you can imagine how much equipment and sensors goes into this. A Navy ship has more than 75,000 to 100,000 sensors in various equipments. Oops, I ran kind of too fast. So it's a tremendous amount of data that's being collected at every moment and has to be analyzed and to optimize processes and make better decisions. So this is kind of the architecture. It's a different view that's how they present it, because they fitted it in a more traditional framework of presenting the architecture, but it's essentially the same as the interrelated architecture that I showed you, because you have the line of business applications, and these can be the partner-based, customer-based, and etc. These are all the different line of business applications, including the external resources, which is becoming an even more important part in today's world. How do you get external data and things? This is the entire data management and information management platform, including here the integration layer. So they kind of, from an IT perspective, gave it a little bit more expanded framework. And these are various tools in the BI platform, from optimize in-memory management, search capabilities, predictive management, performance management. So I want to point out here, it's a lot of components that go just at this center, because this covers, these aspects here cover the BI and data management, kind of the analytics platform. And naturally, you have the presentation layer on the top, which goes from dashboards, online, desktop, and etc., to embedded analytics in operational control systems and external line of business systems. So the flow goes in every possible direction. And that's where it becomes a big issue to have that flexibility to be able to interconnect, disperse, and integrate with it external ones too, because your analytics may come from open source systems, may come from different languages, and etc., but they have to leverage the rest. Otherwise, you'll be building everything from the beginning for every individual project. So the foundation is key. And then their goal is, once you build this foundation, you're able to just add new applications or data products, however you call them, on as needed basis. That's kind of the idea. Create the architecture to be extensible, so there is no problem that arises that you cannot solve within this architecture. So here is the material state management analytics platform, and I want to emphasize here three things. So they have the reporting engine, or the analytics engine. People now have the reporting is now bad word, analytics is the cool word, but they essentially have the same information processed in both. It's the only difference. I mean, you can have as advanced analytics in a reporting engine or otherwise, so terminology. But this goes across the entire enterprise. I mean, this is the amazing part. So their analytics engine, everything that processes information, whether statistically, descriptively, or in any other way, through optimization, goes, I keep clicking, or maybe this clicker is coordinated with the next room. It has happened, and it's quite interesting when it happens. So the key point I'm making here is this covers the entire enterprise. So it gives you a complete view however you want to need it. So it gets a completely again, I think this is coordinated with the other room. You have a completely configurable views from the task group. So you start from the task down to the individual signals and defects. So that gives them the speed of, so to say, discovery and diagnosis and anything else. Again, I bet I'm flipping their slides back and they're flipping them forward. We got in a click battle. When it happened the first time to me, I was so baffled. What is happening? And then you realize it's in the other room. And then, interestingly enough, so it gives you the horizontal scale across the entire enterprise, the vertical scale, the depth of detail that you may need to solve a problem. Okay. Maybe I'll turn this off so we don't get into that problem. And let's take it out. Okay, now we don't have that. And it gives you the lockdown views for, they have lockdown is in essence for security and other purposes, so that, now that's getting interesting, and I'm now curious, how does it happen? The slide has timer? I never knew about it. Oh, okay, that's good. Anyway, so it's extended. The third point is you have horizontal, vertical, depth of detail, and also external. So you're getting it out to the enterprise, to the partners, suppliers, and etc. Now we're on the timer. Okay, I need a few more slides. So this is the maintenance management, and again, this gives you an idea of the approach to get a holistic view from the outstanding maintenance to job concessions to assets concessions. Okay, I have to plug this back. This timer is set to a very small one. To link to live system connections, very important integration. Very often in settings like that, you have to jump from the higher level system down to the very detail. To the job status. Again, it has to give you a complete view regardless of how many systems are there to check on that. And the third component that's very important in this system is the data quality gateway and reporting. And you heard it in the previous talks. I remember, I forgot which one it was, about how important and how frequently people even correct data. We already know that the data is imperfect. And in many cases, it's the engineers and it's the people on the ground that know how to do that. So they created here a really sleek portal that allow the professionals, when they encounter data problems, to fix them on the spot or to create a task for these problems to be fixed. So that's kind of the dynamic learning aspect of the systems when you're looking at everything, and at the same time you're allowing, based on the learning, to create corrections in the system and tasks for corrections in the system. And that's probably one of the very important topics. You should not stop implementing analytics because the data quality is not perfect. It won't be perfect on day one, but as long as you have a system in place that allows you to work on it and to dynamically correct that, you're going to be moving ahead, improving the analytics, improving the data qualities, and improving the decision support. The final one is, what do you do with the big data that's coming directly from the ship? And so a couple of the things there, and low-hanging fruits. I like this because the companies that really succeed in this, they find low-hanging fruits that immediately deliver value. It doesn't have to be complicated. In this case, they're watching the chilling water system, and they're monitoring for any defects in the system. And it's pretty simple analytics, actually, when you monitor just this. There are systems that do not require the full advanced kind of analytics and stuff like that to start doing condition-based maintenance. And how do they exploit the information? That's really important because that tells you about their learning system. They apply these 3 rules to every knowledge project that they start on condition-based maintenance. So they use the information, the ship, to carry out the inspections based on the data. They advise, and this is even more important, they advise on the change in usage. I mean, this is a really, really important learning aspect that people neglect, but it is built into their objectives. They say, if we're going to monitor these things over time and stuff, can we create a better usage pattern than the one we have? Most people are focused on, my time is out. Most people are focused on this, but essentially these 2 are as important as everything else. The final one is consider redesign of the system. They actually keep a scorecard of how many systems have been redesigned based on the data, the usage patterns, and other variables from the data being collected. And with this, I'm not going to argue anymore with the slide timer, so I'm going to open it for questions.